So, I'm here today to talk to you about the reactive data layer, which is essentially an adjustment to your current architecture that will help you manage both scale and your reactive applications. Now, what gives me the right to stand up here? Well, I've spent several years doing a variety of different roles, anything from being the QA guy all the way up to running entire development teams spanning multiple countries. I've worked with the European Space Agency, I've worked abroad, I've run my own show for years, I've been in the consultancy, I've been in about 10 different industries, and I've seen similar problems in all of them. But as Mr. Matt Webb can tell you, because I'm going to pick on him because he's right here in the front, this is one of those things that I've been complaining about for about as long as he's known me, and we finally got an architectural solution that we think will start solving that problem. So today, we're going to talk about the reactive data layer as a term. We're going to look at the enterprise ecosystem and kind of how it's changed. We're going to justify that need and that desire for the RDL. And then we're going to look at some of the solutions out there. Mostly, we're here to just kind of have fun and talk about technology. So, as the caveat, and there will be a little bit of corporate shilling going on, but I work for Push Technology. That's why I'm here in this bright pink shirt. I don't normally wear these things, but it is our official React color. And if you ever want to find me, just look for the bright pink shirt. I'll be wearing another one tomorrow. So what is the reactive data layer? All right, I'm going to jump right in here. A reactive data layer is simply a scalable, bidirectional layer in the stack that abstracts away the serialization and the transmission of data between arbitrary endpoints. Now that's a lot, right? But what we're talking about is a layer in your stack that both produces and consumes data. Because we no longer have a world where we only have consumers of data. Every single device in this room is both producing and consuming data at the same time. Your mobile phone, all your IoT devices, everything, producing and consuming data. So we have to have bidirectional. Because of the influx of all these devices, we also have to have a scalable solution. It's not sufficient anymore to be able to handle 100 users at a time. You need to handle thousands, tens of thousands, even millions. And we all hope to make applications that make money, right? And the way that we do that is we get a lot more users. So being able to handle a lot more users with this intelligent bidirectional data is a big problem. Finally, anybody who's worked in a series of APIs, whether it be REST, whether it be some kind of serialization using Hessian, whether you've built your own, whether you've even used SOAP, whether you've dropped log files and parsed those, there is a very serious concern around serializing the data, deserializing the data, and transmitting the data. There's a number of solutions out there. You've got Hessian, you've got Burlap, you've got Spring HTTP Invoker, you've got JSON, you've got XML, you can drop log files. Most of your CRM solutions will use tab delimited or CSV files. All of that serialization starts to become a real problem. How do you take one endpoint that has multiple serialization technologies? How do you make sure all the data in your system is serialized correctly? So we need a layer that handles all that serialization, handles that transmission intelligently, handles it in a bidirectional fashion and at a scalable point. So hopefully that kind of makes sense. Now, the last thing on here is arbitrary endpoints. Arbitrary endpoints implies that it both communicates with internal systems and external systems, whether those external systems are B2B, whether they're B2C, whether they're mobile devices, IoT devices. You could have external services like your CI, your business intelligence, your CRM, whatever you've got, even your ERP systems. You need a way to communicate with all of that. Everybody's probably familiar with this kind of architecture. I mean, we've probably all seen or at least worked with an architecture that looks something like this. It's just a mess. It's a spaghetti architecture. And the worst part is, this is primarily your back-end business architecture, right? It's just a giant mess. Everything's connected to everything. And when you start looking at your existing infrastructure as a whole, you wind up with a series of devices or applications that are all connecting through your firewall to your web servers, then have to make connections back to your back-end systems, which we just looked at an example of. And those all have to talk to your analytics systems, those have to talk to your BI systems, your ERP systems, your CRM. And when you start talking about all these systems in the cloud-based world we're now living in the software as a service world we live in, those systems can be in another infrastructure. So how do you communicate with Salesforce when they're in a completely different environment? How do you communicate with Dynamics? How do you intelligently talk to your BI system and make sure that all that data is up to date in real time? These complex architecture concerns really boil down to long ramp times for new hires. It's becoming longer and longer. I've worked at companies where the average new hire for development to understand the system was 6 months. Within 2 years, that 6 months was closer to 12 months, and that was to understand the entire thing. And that's not even talking about the architecture. That's just understanding how all the systems interacted. So you need to drop that ramp time because you can't wait that long. You have to be reactive to customers. It's hard to maintain. You now have all these disparate systems you have to scale independently. Speaking of scale, it is very hard to scale. How do you analyze your load and say, oh, the load on this particular web server went up, and therefore the load on my backend system went up, which led to the load on my database going up. So what component do I need to scale? What was causing the block? Was it my web server couldn't handle the connections? Was it my backend was inefficient? Was it my database was actually blocking? And if you scale the wrong thing, you've all of a sudden wasted money, you've wasted time, and you've not solved the problem. And it's very hard to secure. Anybody ever worked with PCI compliance in here? Oh yeah, all sorts of fun, right? And so you know the scope you have to put all those services in to secure them, especially if those services independently scale, becomes a real problem. And it starts to become really expensive because what do these guys charge by? They charge by the number of servers, the number of instances, how much work it is for them. Finally, your security scope in general, not talking about specific to PCI, but talking about security in general, becomes painful. Because even if you use the best tools available, Chef, Puppet, you start talking about virtualization, you start creating images, spinning up servers automatically, you still have to worry about that one security instance. And what happens when you have a day zero instance, when you have to go solve that day zero? You've all of a sudden got to redeploy hundreds, potentially, of different services. Wouldn't you rather deploy tens of services that you know can solve that problem, and then you only have to worry about what the public sees in one layer? Well, that's what we're arguing for when we talk about the RDL, the reactive data layer. So the reactive data layer is simply this layer that exists between every service. You can think about it in a number of different ways, but fundamentally it sits somewhere around where you draw that magical little cloud shape that says this is where we communicate through the internet. It encompasses that. And then it takes all your internal systems with all those internal APIs and encompasses that. So now your BI, if it's internal, if it's external, doesn't matter, can communicate with your CRM, and it doesn't have to know anything about your CRM. Anybody a horror movie fan, Revenge of the Body Snatchers? So you can pull a complete Finney on any of your services. Let me give you a perfect example. Bank experience anywhere? So banks have mainframes. And when I say mainframes, I literally mean computers the size of this room that are about 30 years old, that they haven't updated in 20 years because they're afraid if they turn it off, it won't come back on. And by the way, that's what runs your core business. And if that thing goes down, who knows what's going to happen to your account balance? So scary, right? So how do these guys take these systems that were built for maybe 100 concurrent connections and offer you a mobile app to check your balance, to move money around, to make payments, anything like that? How can they offer that scale? Is anybody happy with the speed of their banking applications? Right? One person. There you go. But there's very few out there who are happy, and it's really a performance problem. But it's a great way to say, look, we can take that mainframe, we can plug it right into my RDL, and then my RDL has a single connection to it. All the data is in and out. Now it becomes a black box. When I've got a black box, I can do a Finney. I can do a Revenge of the Body Snatchers. I can pull that thing out and replace it with something completely different. So now we can take all the concern about updating these systems, and we can black box it, we can make it easier to test, we can make it so much more efficient to update. And so what do we gain? Well, we gain a simplified stack. I would much rather work with something where every single component in my system integrates with one thing. I don't want to have 12 different APIs for my iOS app and 15 different APIs for my Android app and 10 different APIs for my website, unless I'm on the shopping cart and then it's 20 different APIs, all this type of, I mean, I'm getting some nods. I'm sure some of you have seen this. It's not pretty. We get an SOA and microservice architecture support. So if you've worked with SOA, if you worked with microservices, the common response I hear and the common thing I hear about from people who talk to me about this is it's a great concept, but when you start applying it to the real world, it can become untenable. How do you scale those microservices? How do you scale those that service-oriented architecture? How do you make it truly work? How do you really black box things? And out of the box, we're going to start supporting that with the RDL. We're going to provide a single layer of scale. And when I say scale, I don't just mean handle user load. What about global scale? What happens if you write an app that turns out to be the next big thing in Japan? Can you handle scaling over to Japan correctly and making sure the Japanese market is satisfied while the American market maybe doesn't have a lot of use for it? Or Europe? Or what happens if you all of a sudden take off in Europe and you've scaled up in Japan, and how do you do that geoscale? How do you keep all of that in sync? Finally, it makes it a lot easier to secure. You're sitting there talking about a single layer, a single set of servers, and when you start looking at the ability to scale on those proportions, you start to talk about the ability to have fewer servers. So what you can do right now with maybe 100 servers, we can tone down to maybe 10 and do that with 10 different servers. So you're talking about a tenth of the work to harden the servers, a tenth of the work to manage the servers, a tenth of the work to update those servers. Sounds pretty appealing. Lastly, and not least, anybody working with PCI has a really great desire to work with this. I mean, the security scope is vastly minimized when you start to talk about putting a single path through the system. And if all your PCI compliant boxes only have to sit in a very small subset of your architecture, then those PCI boxes now are in scope, and those PCI boxes are what you secure. So who really cares, right? Right now we have three major problems that we're fighting with. We have a problem of disparate systems, 12, 15, 20 different APIs we've got to integrate with, whether it's your analytics, your BI, your CRM, your whatever. You've got irregular scaling patterns. User load is not consistent. I mean, I would hope that your user load is consistent, but most people who deal with the internet don't have consistent user load. They have spikes, they have drops. This is why Amazon makes so much money with auto-scaling. We're also talking about high-performance systems. Nobody wants to wait. Everything has to be instantaneous. And then let's talk about the next big thing. The Reactive manifesto is out there. It's been written. It's starting to be read. Reactive applications are the next big thing. So how do you support reactive applications? How do you handle a system that needs to be responsive to instant changes, but you don't want to poll because the data required to poll will all of a sudden start to overwhelm your systems and you'll lose scale. One of the very important things that Mozilla did, speaking of scale, is they did an analysis of Node.js. So you can't just talk about scale because Node.js can scale, but you need to look at the quality of service behind that scale. So it's not just, can I handle 20,000 connections? It's, can I handle 20,000 connections and still provide decent latency? This is an actual graph from Mozilla. The bottom is the approximate number of connections per second, and the left-hand side is the latency per connection. Now, the point at which we start to see that exponential function take place is about 700 concurrent connections. Anybody happy with 700 concurrent connections out of a single node server? That's great. You have the cool app. So, but if that works for you, wonderful. But that means if you're talking about 70,000 concurrent connections, you now need 100 servers. Did I do that math? 1,000 servers. 100 servers. It's the end of the day. Yeah.
Is that taking into account multi-threading a node environment? In the sense that you can have, you get increased latency because of the node loop of having 70 concurrent users. If you have multiple threads, then that creates multiple queues.
Yeah, I actually don't know. I didn't dig into the study too deeply, but this is what their analysis of the single node server was. Either way, you're still going to wind up with a point at which you reach that exponential curve. And if it's not 700, let's say it's 7,000, you're still going to hit that point, right? So you need to kind of figure out what works for you. And again, let me step back and say everything I'm going to throw at you, everything we're going to talk about today is all based on experiences I've had being generalized. Every single one of you writes different applications that has different needs. And so every single one of these things needs to be tested independently, right? I would never come in and just blindly say, your application, without any testing, is going to handle 700 concurrent connections before it starts spiking. It might handle 50, but it might also handle 7,000. So part of that is about testing. I'm just showing you what Mozilla has put out there, and I've put a link to their article on this. If you'd like to go check it out at some point, I can share the slides. Anybody ever said my site is fast enough? Has your boss said that? I mean, nobody ever says that. Speed is king. Your customers never say it's fast. I mean, occasionally you get the customer that says it's fast enough, but that's not the standard. It's faster than somebody else's, right? And how long will that last? Because there's always somebody coming in to compete. So as your load grows, so does your latency. We just talked about that. Your enterprise ecosystems that we're using to solve this, typically right now, are using some kind of MOM architecture. They're using enterprise messaging, ActiveMQ, IBM RabbitMQ, send data around quickly. But those same solutions can't be used with the internet. We can't take that messaging solution that we've got currently and drop it over the web. It's just not efficient. Those systems were built for very stable, high bandwidth networks. And when you start talking about your mobile device, you're not talking about either. Most people will say, I don't have a throughput problem. And again, I go back to, as we move into a mobile world, the thing people need to keep in mind is we're already talking about big data. Big data has been the next big thing for a long time, right? And big data has reached a point where people are getting so much data they don't know what to do with it. And so we're sending all this data back and forth, and what's happening? IoT is now happening. IoT is coming in, and they're expecting to bring in 50+ billion devices by 2020. Your car, your refrigerator, your microwave, your coffee machine. I'm not kidding on that one. They're actually talking about doing it in your coffee machine because the weather is really important to see on the screen of your coffee machine. But it makes every app developer very much affected, right? Because this is essentially what is going back and forth on the wire. And we all have to pay attention when we see a lot of data moving back and forth. So The Economist did a really good bit a while back about data everywhere. And, well, dropped a grab, I guess. But it's not been historically an issue with any kind of MOM architecture. We've got a lot of systems that internally we can get data moving around back and forth. Your web services have been fast enough because your home bandwidth has been fine. And as we start to move forward, bandwidth is not free or infinite. Not for enterprises, not for consumers. Anybody else pay for the upgraded bandwidth that costs twice as much for maybe a third more? But you do it because you don't want to wait, right? It's never fast enough. And the one thing that drives you nuts is when you go to that one web page that's slow and curmudgeon-y and you just can't get anything out of it. So we're now talking about services over the internet, and you have an enterprise problem too, where you have to move that data over the internet. It's not just in your data center, it's on the cloud environment, and it's cloud to cloud. So our new future really looks at scaling devices not just off CPU and memory load, but off NIC. Because the simple mathematics of it work out as such. Your NIC can only handle so many bits per second. And so if you start sending more and more data, you'll actually saturate a NIC before you saturate a CPU, before you saturate the memory. Right? And it becomes a real problem. So we want to make sure we pay attention to that. Now here's a great thought case. 50,000 concurrent connections, 10 updates a second. That's 1.8 billion messages an hour, equaling 84 gig a day or 31.5 terabytes a year. So 31.5 terabytes a year for 50,000 concurrent connections, doing 10 updates a second. And each message is only 2 bytes. So that's with 2 bytes. Now imagine how much data you're going to start to send if your messages are 64K or 128K. Right? So 2 bytes can make a huge difference off of a nominal number of connections, off a nominal number of updates. So it really matters, this data that we're talking about. Finally, internet sympathy. Having awareness that we're dealing with data that's moving to multiple different devices over the internet, and being sympathetic to the fact that not every single device is going to have the best broadband connection. Sometimes you're going to be dealing with hotel Wi-Fi or conference Wi-Fi or your phone's hotspot or your parents' house where they refuse to upgrade to anything past DSL. So you've got a lot of different variations, and that connection is constantly changing. So you need to have at least a mind towards switching back and forth. Now, what does this play with the RDL? Why am I talking about internet sympathy when I talk about an RDL? Internet sympathy is all about what the RDL is. It's about sending that data to arbitrary endpoints. Those arbitrary endpoints could be a mobile device. It could be an IoT device. And you want to make sure that you're paying attention to all of the factors when you're considering whether or not an RDL works for you. So an RDL is supposed to be designed to solve these types of problems. So where do we go from here? The RDL is more of a concept or an architecture. It's really time for you guys to implement the RDL yourself. And forgive me, the power seems to be going. This is what happens when you use a device all day. But you can have 2 choices when you start to look at an RDL. Right? You can either choose to implement it yourself. There's nothing stopping you from doing that. I mean, it's simply a concept, an architectural design. Or you can buy one. There's several providers out there that will do different things to help you manage your data in a stateful way as it connects to arbitrary endpoints across the internet or your infrastructure. But when you're looking at that and when you're considering it, be also sure to consider things that we haven't talked about that we don't feel are inherent to the RDL but are added bonuses. Things like security and device agnosticism. Now security, when I say security, I mean DDoS, I mean man in the middle. I'm not talking about the inherent security that comes in RDL when you talk about scope, when you talk about easier to manage. And device agnosticism plays really well into internet sympathy, about you have multiple devices. So that gives us an RDL checklist. So if you're going to build one, make sure it's bidirectional. Make sure it's scalable. Make sure it's agnostic to your devices, internal systems, external systems, BI, CRM. Abstract the transmission of data and abstract the serialization of data. Because those are the complicated things. Those are the things we want to put in a single layer. That brings us to security. I've been at a few companies, and I could tell you some horror stories. Your space program in Europe, you don't want to know, right? You do not want to understand how their security model works. They're so afraid of people getting in through their firewall, they open up one port, and that's directly to the database. Yeah. This is the power of the European Space Agency. And they somehow managed to land that probe on the asteroid. But yeah, thank you for the Europeans in the room. So we do want to make sure we talk about security a little bit, because this is something we need to also consider when we talk about the RDL. And I'm building to a very specific point, I'm sure. We have the man in the middle. Everybody's probably heard of it. mostly understands it, maybe, no, yeah, kind of. Man in the middle is about somebody sitting between a user and the server. They're reading the traffic, and even when you're encrypting things over SSL, you need to be careful because you're encrypting the headers too. And if anybody read Google's Speedy white paper, about 70 to 80% of the headers on a given site are identical. So if you take known quantities over time and you apply them to an encryption algorithm that needs a key, then with enough patience, time, and effort, you have the potential to pull that key. It's not easy. It's not something that everybody's going to do, but it does offer a bit of a concern. So pay attention to that when you start talking about things like the reactive data layer. Also look at things like DDoS. And I put up two really small companies that I don't know if you guys have heard of or not, Best Buy and Twitter. But both of these guys suffered from a very serious outage because of overcapacity, right? And essentially, the DDoS is just meant to overscale a system. So what is the RDL designed to do? The RDL is designed to handle extreme scale. So implement an RDL and watch your site laugh at DDoS. And I say that because I have a little bit of a corporate shill to give you. We do have a cloud product, and I can give you a number of different use cases specifically for this product, but it is the first time you're talking about real-time data services delivered via the cloud. It is unmatched in scale and speed. It has lower costs than pretty much any competitor with reduced risk because it was designed for the internet, and it was tested in the enterprise, and now it's available in the cloud for everybody to consume. By the way, it's free. We got a free tier, so everybody can go out and check it out and play with it. So, React. When I say laugh at DDoS attacks, I do mean that. We've had clients who have gone through a number of DDoS attacks, and every service went down except for ours. So we just sat there and laughed.
So when you say that, like, it keeps the site from going down, but are you paying for increased usage or something with that? Because you're still servicing that many requests. Like, is there a cost for say,
Sure.
a consumer of React?
Absolutely, absolutely. So in that type of situation, you would have a consumption base where you either hit a natural limit on users or bandwidth. But you're going to be able to keep the site up and running because the system is designed to essentially break the exponential function of the latency curve. Through independent testing, we've seen that we have the same latency at 0 connections, 1,000 connections, and 20,000 connections as about 50 milliseconds for round tripping. And we've done a number of different tests doing things from California out to the Europe and back. We can average about 200 milliseconds of latency time. And what you tend to see is because we're built for such extreme scale, what's your node server running on? Or Java server, whatever your servers, what's your enterprise server class?
On Ubuntu.
8 core, 4 core, how many cores?
Oh, like for the enterprise stuff?
Yeah. 4 cores, 8 gig of RAM.
Yeah.
So we've seen in excess of 70,000 concurrent connections on a box like that. Yeah. So that's what I'm saying when I'm talking about extreme scale, right? Is you can take that node server that's running 700 or even 7,000 if you happen to tune it right, and you compare that to 70,000 off of some of the stuff we've done, and it's really hard to start comparing it. Now, I don't want to stand up here and do nothing but shill. So I'm going to try and talk around the product. If anybody has any questions, I encourage you to take my card. I encourage you to reach out. My colleagues, Peter and Ross, are here as well. We're all happy to answer any questions you have. But let me give you a couple of use cases. And these come out of our customer base, but they could apply to any of your customers, right? These could apply to any of your use cases. Because our first use case comes from the world of online betting and gaming. In online betting and gaming, especially in Europe, there is a big day of football, soccer, and other sporting events, and that's Saturday. So what we have on Sundays here with our football, they have on Saturdays. Only they have a lot more games. We had a company who was having a serious problem with their database. they were using some extremely large servers, 32, 64 core type servers, massive amounts of RAM. And every Saturday, the whole team would show up at 8 a.m. By noon, they're struggling. By 2, they're down. Every Saturday, without fail, with the whole entire team on site. And so what happened was their database server just got overloaded. So they put in diffusion in front of that, an RDL. And the RDL handled that scale. And then it offloaded that to the database as quickly as the database could handle it. Now they have their Saturdays back. Actual quote from their CTO, they have their Saturdays back. They have one guy on call, nobody gets called in, everything just works. Here's another one. Another online betting, talking about extreme scale. These guys had a requirement that they wanted an ad so small that it would be classed as a static advertisement with real-time, up-to-date odds. They also wanted those odds to appear real-time on the television, on the website, on their mobile browser. So we went in and put in a reactive data layer. The reactive data layer solved that problem. And now they deal with over 2 million concurrent connections every week with real-time statistics on the TV, in an ad, on the browser, wherever.
So does this act like a CloudFront layer or like a capsule or something like that in order to kind of be an edge layer of protection on the servers, or is it more of a buried in the infrastructure?
It's middleware, so it sits in the infrastructure, and then you use client SDKs to consume it within whatever you'd like.
Okay.
Does that make sense?
Yep.
Another example, connected car. This is a great IoT one. And as cars get smarter, we were looking at a company that was doing a connected car demo. They wrote their own modifier, and they were taking the cars, and they were dumping all the data from the cars into a database, and then running a dashboard off the database. In this particular example, they ran about 7,000 concurrent connections, and they were dumping 1,000K per second per connection into the database. They'd click lock on one of the cars. It'd take 15 seconds to show up on the dashboard. Not surprising, right? They're saturating everything. So we put the RDL in. They scaled up to 30,000 concurrent connections without any trouble. And they were doing sub-second response times on the dashboard. Because the dashboard then fed off the RDL, the database wasn't overloaded, and it was the same hardware. We're talking developer hardware, 2 4-core machines, or 2 or 4 core machines, 8 gigs, 4 gigs of RAM, small machines. Finally, there's a great one in online gaming, moving data around. You have geoscale and bandwidth conservation. So these guys were moving data from Gibraltar, which I don't know how much you guys know about Gibraltar, but the price of moving bandwidth around in Gibraltar, because there's a monopoly on the infrastructure, is about 100 times what it is anywhere else in the world. So moving data out of Gibraltar cost them about 100 times anywhere else, and they had to move all of this data to London. And they were trying to keep that data in near real time as they could. So what they did was they snapshot the data every 7.5 seconds, move it over to London. And they were figuring they were doing about 3 to 6 meg of data, depending on the volume of traffic they had. We put in the RDL, and now they're looking at instantaneous updates in London. They're looking at a 90 to 95% bandwidth reduction. So 90 to 95% bandwidth reduction in one of the most expensive places to move data in and out of. Which all of a sudden, because we go back to our NIC conversation about a simple mathematical conversation around the number of bits per second you can send, if we're reducing the amount of data you're sending by 85, 90, 95%, then all of a sudden we can either send more messages or we can have more connections because the NICs can handle it.
So, if I understand correctly,
Sure.
the backend servers are still the same, and they have a lower capacity limit. Does that mean that the reactive data layer is not really real time and it's just kind of preparing and queuing stuff?
Well,
It's just optimizing and handling the load, or is it doing something different?
so it does a real-time state of the data. So as your back-end system processes the data, and if you run through the workflow, you would look at something like, if you look at something like a transaction going through, a transaction would happen, it would hit the RDL would then pass that transaction back to whatever service needs it. And more specifically, it would pass it to whatever service or services are interested in it, because it could be your CRM wants to know when a transaction is attempted, and when it succeeds, but your payment system actually needs to know when the transaction's been attempted. And maybe your BI needs to know too, right? So it's going to send all of those, and then when the payment system has completed the transaction, it'll update the RDL. The RDL will, at the same time, send it out to the client with a verification. It'll send everything out to the BI, the CRM, all the other internal systems. And so if there needs to be an action like an emailer that goes out based on that, it'll send it to the emailer fires off. So because you're taking all that load and putting it in one place, you're really only talking about a series of if you've used ActiveMQ or RabbitMQ or any kind of messaging bus, best way to think about it is like a topic structure. So you're essentially creating a topic structure and saying, this is what I'm interested in, and when things change, you use a publish-subscribe model rather than a request-response model to push the data rather than require the server pull for it. Make sense? So we are going to attempt a live code demo. So keep calm. We will see how this goes. Now, what I put together was we have these two servers, or two web pages, talking to the reactive data layer using React, because it's just a natural thing for me to integrate with. So when I change this, it's going out to the internet, it's going back to the system, and it's updating it in both places proactively. And the only data it's sending is whatever I put in here. So anybody got a favorite color?
Lemon chiffon.
But we can essentially put any color we want in, and it will send that out to the server. And then the server is actually sending it back to its own web page, as well as the secondary web page. Now, what's the code for this look like? Where's my mouse? And let's see. Of course, I can't blow that up. All right, we can see that a little bit better. So, a lot of boilerplate HTML, but all we're doing to do this reactive data layer, and this is the consumer, is this simple: we create the connection, we subscribe to a specific topic, and then whenever the topic updates, we just update it. We update the object.
What mechanism are you using to do this pub/sub paradigm? Is this WebSockets or what?
So this connection will be over WebSockets. The React itself is built so it can cascade. So depending on what service you're using, if you're talking Java, .NET, C, anything like that, you can actually use a TCP connection. But most of the web is going to use WebSockets. Or we can cascade down to things like HTTP-C or long pull, just to actually get some of the older browsers that don't support WebSockets. Code demo worked. So this is all the code. I mean, you are actually looking at all of the code it takes to create that. And I can start modifying different values by simply saying, over here I want to subscribe to a different set of topics, and then do whatever I want with the data. Over here I just have to update a different set of topics based on user input. So now take an RDL where you can push that data in, and you can use some kind of intelligence like BI in the background to process that data and then throw more data back in the RDL, which can then be consumed by a dashboard. All near real time. Faster than the eye. I mean, your eye can only detect, what, about 400 or 500 milliseconds? So as long as we can beat that, we should be good, right? Fast enough. Okay, so that about ends what I've got. I want to kind of thank you. In summary, please do take my card. Please do check out React. It's kind of an interesting architecture, but even if you don't want to take that away, do consider the RDL. Because I think in 5 years, everybody's going to sit down and whether they call it an RDL or not, we're seeing people do this all over the place. And my job is basically go around and talk to all sorts of different companies, do all sorts of different things, and figuring out how to solve their problems. And we're seeing a lot of companies do this, whether they call it an RDL or not. And I'm hoping that you guys all take this and start using it yourselves. Any other questions? Thank you so much for your attention, guys.